Assalamu alaikum warahmatullahi wabarakatuh. In today's video, we will learn about how we can measure the synchronous generator model parameters. So, the equivalent circuit of synchronous generator contains three quantities that must be determined in order to completely describe the behavior of a real synchronous generator. So those three values are the relationship between field current and flux, and therefore between the field current and EA, that's the induced voltage, and the synchronous reactance, the armature resistance. So we can perform certain tests to find out these values. Let's look on these tests. So the first of all, we can do the open circuit test, and in this the generator is turned at the rated speed with the prime mover, and the terminals are disconnected from all loads. So there is no load connected to the generator. Now the field current is set to 0. And then the field current is gradually increased in steps, and the terminal voltage is measured at each step along the way. So for different values of field current, we can have different values of the terminal voltages. So because the terminal voltages, the generator is in no load condition, so the current that is in the armature will be 0. So E is equal to the phase voltage. So it is thus we can have the plot between the IF which is versus VT, or we can say that it's between EA because of this open circuit. So we can see here that this is approximately a linear curve up to certain range of the field current, and then it just goes off from the linear track. But we can assume it as by this dotted line as this is our line gap. So these actually characteristics are known as the open circuit characteristics of a generator. So next we can perform the short circuit test, and in this short circuit test, what we do is that we adjust the IF to 0 and short circuit the terminals of generator so that the maximum current will flow, and then V phase is obviously 0 because of this short circuit. Now what we will do is that we will measure IA, or the line current IL, as IF is increased. So again here we will increase the IF carefully because we have the terminals shorted, and we will measure the armature current. And this plot is known as the short circuit characteristics. So the armature current while terminals are short circuited is then IA is equal to EA over RA plus JXS. So here from this circuit we can see that this is equal to this, and similarly ZS will be equal to RA square plus XS square, which is equal to EA over IA. Now here V phase is 0, so we will not get any V phase, but we can have it with further reference, so that IA RA will be just added here, and then we have this JXIA, and this EA will be our resultant induced voltage in the armature. Now from here, how we can calculate these parameters? So an approximate method for determining the synchronous reactance XS at a given field current is, so remember that you have to be careful while calculating that the field current must be the same for measuring from the open circuit characteristics and the short circuit characteristics. So how we can do it? That from the first step, that we will get the terminal voltage EA from open circuit characteristics at a particular field current, and at the same current from the short circuit current flow IASC at the field current from short circuit characteristics. So what we'll get is EA from the open circuit characteristics. So suppose that if field current is suppose 1 ampere, and at the same 1 ampere we will see what's the armature current from the short circuit characteristics. If we just go back and look here, so we can see that if we say that here it is approximately 1 ampere, so we will get this EA from this open circuit characteristics, and then from short circuit characteristics at the same IF, which is 1 ampere here, so we will get the IA armature current at that. So access will be then simply EA over IA, which is equal to V phase open circuit by IA. So the RA can be approximated by applying DC voltage to the windings while machine is stationary and measuring resulting current flow. Simply by applying the Ohm's law, we can find out this RA by just applying the DC voltage to the winding. So we can have these two parameters, XS and IA. Now let's look at that, how these generators operate while they are even connected, while they are working in standalone operation, or they are working in means if you have the multiple generators. So the behavior of a synchronous generator, first we will look at that if the generator is operating alone, standalone condition, that there is only one generator and all the load is connected to this generator. So the behavior of synchronous generator depends upon the power factor of the load, because the power factor, it could be leading power factor load, lagging power factor load, or the unity power factor load. So standalone or parallel operation, that what we have seen, but for first we will look for the standalone operation. So now first we just ignore the effect of RA so that we can have our analysis easy. Unless otherwise stated, the speed of the synchronous generator will be assumed constant because of the frequency that we have seen previously. So we have to keep the speed of the synchronous generator constant. And the rotor flux in the generator is constant unless their field current is explicitly changed. Obviously, because the flux in the rotor is dependent upon the field current that we are applying from externally. Now what happens on the synchronous generator operating alone, if we increase or decrease the load? So if we increase the load, or we put in more load while it is operating, so increase of load is an increase in real and reactive power. Obviously, because of the power triangle, we know that power load could be real or reactive. So such a load increase the load current drawn from the generator. So if you put the load on the generator, obviously it will draw more current from the generator. So here we have some assumptions that the field resistor has not been changed and field current is kept constant, hence flux is constant and RF is constant. So IF is constant, it means that the flux that is producing from the rotor is also a constant value. So generator rotor speed omega is maintained constant, obviously for the frequency constant reason. Therefore magnitude of EA will be simply k phi omega, and that will obviously be a constant because omega is constant, phi is constant. So k is already a machine parameters constant, that's always constant. So if EA is constant, what actually varies with the changing load? So let's look at this. So if we have the lagging load, what will happen? IA obviously will increase the armature current. That's the current we are obtaining from the stator of the synchronous generator. So it means that here, because the theta is constant, and JXS IA is increasing, because IA is increasing, phase remains the same. As EA is equal to V phase plus JXS IA, EA is constant, so JX IA must stretch between V phase and EA. So here we can see that now we have this V phase previously, and now we have this V phase prime, and what happens that here JXS IA, that is actually stretching. So here we can see that this is JXS IA and this is new JXS IA on the constant. Here we have this locus of EA, because EA is a constant. This is the constant EA locus. So only element which would change to compensate would be the phase voltage. So here we can see that the phase voltage is changing at the terminals. So from the phasor diagram, there is only one point at which the armature reaction voltage can be parallel to its original position while increasing in size. So at lagging power factor, the increase of load current will decrease the terminal voltage significantly. So here we can see that this was the previously, and we have some already lagging load, and we have put another load on this generator. So the terminal or the phase voltage will also reduce here. So similarly, we can see that what happens if we are operating at the unity power factor load. Obviously, the load will increase the IA, and similarly here the obviously EA is constant, so V phase will change, and we can see that for the real power only load, that is the change in this phase voltage is very small. So what happens at the leading power factor? Again, this EA will be constant, and this JXS IA will be stretched up. But again, we can see here that for the leading power factor load, if we increase the leading power factor load, what will happen that the phase voltage will be increasing as compared to the lagging power factor. But the change in these phase voltages in the leading power factor and unity power factor is small compared to the lagging power factor. So let's look at this very important terminology, voltage regulation. So as the load on the generator increases, the terminal voltage drops. Lagging and unity power factor load cases, as we have seen in the phasor diagrams of these lagging and unity power factor loads. However, in practical, it is best to keep the output voltage of a generator to be constant. So obviously, we don't want that voltage to be varied, just like if we are at home and we are using suppose 220 volt. So we don't want that voltage to be changed very much. Although that's been maintained constant by different transformers and the grids, but still at the generation point we also want to keep that voltage constant, because that change in the voltage at generation point will also be reflected in the distribution. So the excitation on the machine is varied, or input power to the generator is varied. So EA has to be controlled, which can be done by controlling the field current IF, or varying IF will vary the flux in the core, which will then vary the EA accordingly. So it means that EA has to be adjusted to keep the terminal voltage constant. So we have to maintain this EA such that the terminal voltage remains constant. And obviously, for adjusting the EA, we have to change the field current accordingly. So the voltage regulation can be defined as that V no load minus V full load by V full load into 100%. So if a synchronous generator operates at a lagging power factor, the voltage regulation is very high. So positive voltage regulation. If synchronous generator operates at unity power factor, just small positive VR, a leading power factor VR is negative. So ideally we want to keep this voltage regulation to be 0, but since the load is unpredictable, we can have either inductive load or capacitive load or whatever, or the resistive load. So in that scenario, we never know that how it's going to change. So accordingly, if the load varies, there is automatic voltage regulators which actually maintain this IF such that we have the terminal voltage is maintained at the constant value. So what's the procedure? That recall that V phase equal to EA minus JXS IA, and here we have ignored the RA. So and also we know that E is equal to K phi omega. So decreasing the field resistance will increase its field current. So we can decrease the field resistance, which we have added to the synchronous generator externally. So since the frequency omega should not be changed, then flux must be changed. So the increase of field current will increase the flux and increase the EA. and the V phase will increase for such that we have the constant voltage at the output. So I hope you have understood up till this point. If you have any question, please feel free to ask. Assalamu alaikum wa rahmatullahi wa barakatuh.